So the last topic we will cover on parameter forms, so-called simultaneous diagonalization. It's about, again, diagonalization, but let's say we have two matrices, and we wonder if we can find a basis so that in that basis both matrices are diagonal. Okay. So let me just write down the theorem. Okay, now let's leave in a finite dimensional vector space and S and T are operators on V. Assume that both S and T are diagonalizable. So that's part of the assumption. We wonder the following. Then there's a basis data for V, so that the matrix representation of T and S are both diagonal. So we have a basis which makes both operators diagonal. Okay. We call this simultaneous diagonalization. We have a basis which diagonalizes both operators diagonal if and only if S and T commute. In other words, S and T is the same as T times S. Okay. So if these operators commute and if they are both diagonalizable, then we can find a basis which makes both operators diagonal at the same time. In this case, we say that S and T are simultaneously diagonalized. In this case, we say that S and T are simultaneously diagonalized. Let's see the proof. So let's prove the first implication. So I assume that there's a basis which makes both S and T diagonal. So assume that there is a basis. Data for the vector space so that both matrices representations of the operators are diagonal. Okay, both of them are diagonal. What we know about diagonal matrices, of course, if you have two diagonal matrices, then they commute. Okay, so diagonal matrices commute. Okay, note that if V1 and V2 are diagonal matrices, then V1 times V2 is the same as V2 times V1. That's not true in general, but for diagonal matrices, of course, of the same size, they commute. Okay? Buna herkes inanıyor mu? Diagonalse commute ederler. Değil mi? Yani çarpıp göreceksiniz. İnanmıyorsanız. İnanmak zorunda değilsiniz tabii, yani hoca öyle diyor diye. But then, let's see. Okay. Then the matrix representation of S times T. What I mean, of course, is the composition of these operators. Okay. So let's, of course, that can be written as what? The matrix representation of S and the matrix representation of T. But these are diagonal matrices. Since they are diagonal, I can write it this way. I can just switch the operator. So here, this is since they are diagonal. Okay. But this is the same thing as the matrix representation of P times S. So what we see is that the matrix representation of S times T and T times S in the same basis are the same. Thus, hence, S times T is the same as T times S. Okay. So this proves one direction. If they are simultaneously diagonalizable, then these two operators commute. Now let's assume this. So now assume that S times T is equal to T times S. Ne yapmam lazım? We must find a basis in which both operators are diagonal. Okay, so we must construct a basis. Okay, we must construct a basis data so that both this operator and this operator, I mean matrix representations are both diagonal, are diagonal matrices. Okay. How can we do this? Well, now, we assumed, of course, in the assumption of the theorem, both operators, right? Both operators are diagonalizable. Okay, that's the starting assumption. Both of them are diagonalizable. both operators are diagonalizable. Now, therefore, S is diagonalizable in particular. So let's choose a basis. K seçelim. Since P is diagonalizable, there is a basis. Basis data. Let's say V1 up to V4 of V in which P is diagonal. So these are eigenvectors of T. This means what? T times Vi is just some element of the field times lambda, like for some lambda I in K, I from 1 up to n. Right? These are eigenvectors for T, and lambda i's are eigenvalues. Of course, there is no guarantee that these VI's are eigenvectors for S. And it is not true in general. They don't have to be eigenvectors for S. But there's still, not too far from being eigenvector for the operator S. Okay, now let's see this. Okay, note that S times T times Vi is equal to what? This is just since S and T are since they commute, right? We assume that S times T is equal to T times S. So instead of S times T, I can write T times S Vi. But you see, for the left-hand side, T times Vi is just lambda I times Vi. So I have lambda I times Vi is equal to T times S times Vi. So this means bunun sonunda da S var. S'i de hatta şöyle yazabilirim. Because since this is linear, I can just take lambda I outside. So what we see is this. T times S times Vi is just lambda I times S times Vi. Therefore, S times Vi is in the eigenspace of T corresponding to the eigenvalue lambda I. And thus, S times Vi is in the eigenspace W lambda I for the operator T corresponding to the eigenvector, eigenvalue eigenvalue lambda. Yani WI dediğin şey, so WI is just this. To the set of all vectors, so that T times B is just lambda I times. Okay? The eigenspace of T corresponding to the eigenvalue Vi. And what we have seen is the following. Vi comes in this digit, and we have seen that S times Vi is also in this subspace. And these VIs, you know, they are linear independent vectors because they form a basis. Therefore, the eigenvectors which lies in this eigenspace is a basis for this subspace, and S maps those basis elements to again to the same subspace. Therefore, I may just consider S as an operator on this subspace because it maps basis elements of this subspace to again to some elements in that same, you know, subspace. So, hence S of W lambda I is contained in this subspace for each I. Right? In other words, I may consider S restricted to the subspace lambda I as a linear map from W lambda I to W lambda I. Değil mi? Yani bu alt uzayı, bu alt uzayı. Normalde bu rastgele iki operatör için geçerli olmaz. Hani birinin eigenspace'ini diğeri korumak zorunda değil. Ama bunlar commute ettiği için bunu sağlıyorlar. Peki, biz ne biliyoruz? Well, we know that S is also diagonalizable. T was diagonalizable, and I used that fact to write down the basis beta, right? We use the fact that T is diagonalizable to write down this basis for T. But S is also diagonalizable as an operator from D to B. And I consider its restriction to the subspace, and it is still diagonalized. Okay, now, since S from D to B is diagonalizable, its restriction to W lambda I, what is that operator? S restricted to W lambda I. It's an operator from this subspace in itself, is also diagonalizable. Burada bir iddia oluyor. Yani bir operatör diagonalizable ve bir tane alt uzayı koruyorsa, hani bir alt uzay var, o alt uzayı kendisine götürüyor. O zaman bu operatörü bu alt uzaya kısıtlarsam o da diagonalizable. İnanıyor musun? Okay. That's true, but yeah, need some truth. Aklımda hazır bir ispat yok ama düşündüm. Evet.
Mesela atıyorum S ve T 3 boyutta olsun. Şu W, yani şu subspace W lambda I'da mesela bir boyutlu olsun. Bir boyutun içerisinde bu üç boyutlu şeyler nasıl devam edecek?
Nasıl?
Yani şey demek isterim. İşte S ve T normalde üç boyutlu.
Tamam. Onlara kısıtlanışını alıyor. Şu hani operatörü bu bir boyutlu nesneye kısıtlıyor. O operatörü. Evet, o. Bu kısmı ama şimdi bunu kabul edin ilk önce. Şimdi aklımda bir ispat yok. Let's assume this. Well, since it is diagonalizable, there is a basis in which this restriction is diagonal. So there is a basis for this subspace beta I for W lambda I such that the restriction of T, not T, I'm sorry, S to this subspace lambda I in that basis lambda beta I, let's say, let's call this di is diagonal. Well, for each lambda I have such a basis, right? Now our vector space D, right, is a direct sum of these subspaces because, let's say, lambda K, I have, these are eigenspaces of the vector space B. These are eigenspaces, sorry, for the operator T. And since T is diagonalizable, this eigenspaces spans the whole vector space, right? And for each one, I have a basis, beta 1, beta 2, beta K. And we have seen that this basis also diagonalize S, okay? So let beta be just the basis beta 1, beta K. Let me say not beta, but beta 1, because I have already beta there. So this is a new basis, okay? Not necessarily the basis over there. The subspaces, of course, are the same, but I choose possibly different bases for the subspaces, and we form a basis by taking the. This is still a basis. Why is it? Because they correspond to distinct eigenvalues. Here, of course, these are distinct eigenvalues. Her bir eigenvalue için bir eigenspace var. But then, of course, this is a basis in which both S and T are diagonalizable. Then both and S are diagonalizable. Neden? Çünkü zaten bunlar WI'nin içinden seçildikleri için bu bazda zaten T diagonalizable, ama ben bunları öyle seçtim ki S de bunların içinde diagonalizable. Okay. Şimdi bir tane örnek yapalım bunlarla ilgili. Okay. One example. For any theta real number, consider the rotation matrix. Or operator, you can also consider as an operator. On R2, given by this cosine theta minus sine theta, sine theta, cosine theta. Okay. Show me. So they are simultaneously. Diagonalized. Over the field. Although these matrices are real matrices, they are not diagonalizable over real numbers. They are diagonalizable only complex numbers. Because these are rotation matrices. They don't have any eigenvector, real eigenvector, right? They rotate every vector. So there's no eigenvector. Eigenvector means that vector, right, should stay in the same direction. Should be mapped to a multiple of it, but the direction shouldn't change. However, this matrix just rotates the whole plane, so no vector is fixed. Everything is turned. Therefore, these are not diagonalizable over real numbers, but over complex numbers, they are diagonalized. So, can you see? Let's find the characteristic polynomial for this. I'm sure şey yapabilirsiniz. Not that, R theta 1, R theta 2 is the same as R theta 2, R theta 1. So they commute for any R theta 1, for any theta 1, theta 2. Why is that? Well, I mean, you rotate the plane theta 1 radians, and then you rotate theta 2 radians. That means you rotated the whole plane theta 1 plus theta 2 radians. And that is, of course, the same thing if you would just rotate first theta 2 radians and then theta 1 radians, right? Rotations commute. İlk önce 30 derece, sonra 40 derece döndürdünüz. Toplamda 70 derece. 70 nasıl yani toplarsanız toplayın. Önce 10, sonra 60 olur. Önce 40, sonra 30 olur. Hepsi aynı şey. Değil mi? Önemli olan toplamda kadar. So, this thing is just R theta 1 plus theta 2. So we claim that these are diagonalizable over the same basis. There's a basis in which they are all diagonalizable. Now let's find out what's the characteristic polynomial of this field. So f of x, what's that? So determinant of x times identity minus r theta. And it is just the determinant of x times identity minus r theta. So x minus cos theta, sine theta, minus sine theta, and here I have, okay, x minus cosine theta. What is the determinant of this? It is just x minus cosine theta squared minus plus sine squared theta. So it is just x squared minus 2x cosine theta plus cosine squared plus sine squared, which is just 1. This is the characteristic formula. What are the eigenvalues? So I have to equate this to 0 to find eigenvalues. Okay, so what are the roots of this polynomial? Okay. They shouldn't be real roots, right? Because we know that this operator doesn't have any real eigenvector. What are the roots? So let's say lambda 1 and 2 roots of this. So they are just 2 cosine theta plus minus b squared b nedir? 4 tane kosinüs theta. Pardon, 2 kosinüs theta. B kare 4 tane kosinüs kare theta eksi 4 şu değil mi? Bölü 2. 4 plus cosine theta plus minus. Burası da nedir? Eksi sinüs 4 tane eksi sinüs kare theta. Kareköklü olursanız eksi olduğu için iyi gelecek. Sinüs theta değil mi? Artı eksi 2 sinüs theta 2'ye de böldük. Sinüs theta. Okay. So we have 2 eigenvalues. One of them is cosine theta plus I sine theta, and the other one is cosine theta minus I sine theta, which is just lambda 1 conjugate. 2 eigenvalues. So for each theta, we have different eigenvalues, right? Eigenvalues are different. But what about the eigenspaces? Let's see. Since the operator,
Hocam kamera kaldı.
since the operators commute, for any theta 1 and theta 2, I should be able to find the basis in which both r theta 1 and r theta 2 are diagonalized. But actually we will do more. I will find the basis in which all of these rotation matrices are diagonal. Okay? In that basis. So let's do that. Let's find the eigenspaces. Let's find the eigenspaces. Okay, W lambda 1. So that is what? That is the set of all vectors in C2. I consider this operator over complex numbers, not from R2 to R2, but C2 to C2, 2 by 2 matrix. Right? Any real number is a complex number. So A, not A, R theta. V is just lambda 1 times V. Okay, so R theta V is lambda 1 times V, implies R theta minus lambda 1 times identity V equals 0. Yani R theta'dan lambda 1 çarpı identity çıkartacağım. Peki, yani kosinüs theta eksi lambda 1. Lambda 1 neydi? Neyse, lambda 1 çarpı lambda 1 dedim şöyle ilk önce. Şey yapayım, adım atmamayayım, şöyle tek tek yapayım. Şurası eksi sinüs teta değil mi? Sinüs teta kosinüs teta eksi lambda 1. Evet, bu matrisli olacak. Lambda 1 neydi? Kosinüs artı i sinüs teta, yani minus I sin theta minus sin theta and again minus I sin theta, and well, these are basically the same, right? Let me just interchange the two, sin theta minus I sin theta, and then just multiply the second row by I and add to this one, you get 0, 0. So what is the equation? So I multiply this by some AB. Yani şöyle yazayım isterseniz, sinüs theta eksi i sin theta 0, 0. Aynen vektörümüz AB olsun. 0, 0. So we get just A times sin theta minus I times B times sin theta equals 0. So I can just let A to be 1 and B to be I, right? Yok, minus I daha iyiymiş. Şöyle. So our eigen vector is just what? The vector spanned by, so V is just AB 1 and minus I. So this is spanned by 1 minus I. Okay. What about the other eigenspace? Well, W2. Well, W2 was W1 conjugate, and our operator is real, so R theta V is W2 times V, which is that lambda 1 bar V, and you consider this, right? Lambda 1 bar times identity V equals 0. The vector you would get here will be just the conjugate of this. So 1 minus I conjugate. What is the conjugate of this? It is just 1 and I. So this is the vector space spanned by 1 and I. Neden? Çünkü şöyle yapın. Just take the conjugate of this equation. R theta minus lambda 1 conjugate identity times V equals 0. Take conjugate of this. So you get what? R conjugate. R is a real matrix. Its conjugate is just R theta minus lambda 1 conjugate, and then you take another conjugate. Well, that is just lambda 1 identity V bar. Well, so V bar is an eigenvalue for lambda 1. So V bar is an eigenvalue for eigenvector for lambda 1. Therefore, this should be just a multiple times 1 minus I. But then what is do? I can just take, let's say, as a base element, V bar 1 minus I. So what is V? It's conjugate of this one, so it is just 1 I. Okay. So what we have obtained is the following. I have obtained eigenspaces. So W lambda 1, which is just spanned by, okay, this vector 1 minus I, and this one 1 I. But you see that these are independent of theta, right? There is no theta here. So they work for all theta. So these are eigenspaces for R theta. For any theta, for any. This means that I have found a basis, and in that basis, all these rotation matrices are diagonalizing. Değil mi? Theta yok bunun içinde. Bazın içinde theta yok. Hepsi için çalışıyor. Yani şöyle yazabilirim. Note R theta in this basis, let's say beta being this basis. 1 minus I and 1 I. So this is the first basis element. This is the second one. So here I will have lambda 1, and here I will have lambda 2, which is so what was this? This was cos theta plus I sine theta. 0, 0, and this is cosine theta minus I sine theta. The diagonal matrices are different. They depend on theta, clearly, but the basis which diagonalize all of them is a common basis. It is independent of theta. Okay. Well, I guess I have like 5 minutes. So this is the end of the maybe sometime I'll talk about the rational form. Well, it is another canonical form. Suppose you wanna diagonalize your matrix over rational numbers, and the characteristic polynomial is irreducible. It can be any degree, right? Over rational numbers, you may have irreducible polynomials of any degree. Atıyorum mesela x küp artı x kare eksi x artı 5. Ama bunun reel küpü var. Ama Q üzerinde olmayabilir. Var mı? Diyelim ki irreducible olsun. Karakteristik polinom bu çıkıyor. Bunun yani eigenvalue'su falan yok. Kompleks sayılarla çalışmak istemiyorsunuz. Hani Q üzerinde çalışmak istiyorsunuz. O zaman sizin ne diagonal formunuz var, ne Jordan formunuz var. Bu durumda rational form diye bir şey var. Yani bu operatörünüzü şöyle bir şey yazabiliyorsunuz. Her yerde yazayım şimdi onu. Aslında yazamam da. Şurada bir yerde yazacağım. Böyle bir şey yazıyorsunuz. 0, 0, 0, 0 minus A0, 1, 0, 0, 0 minus A1, and and then zeros. So ones comes like this, and then the final entry is just minus n minus 1. If the characteristic polynomial is a0 plus a1x n minus 1 x to the power n minus 1 plus x to the power n. Suppose this is your characteristic polynomial, okay? Then you can find the basis in which your operator looks like this, and this is called a rational form for t. Of course, this is not as good as a Jordan form or diagonal form because you have, several non-zero entries here. But besides this, it looks simple. And it is basically the best thing you can obtain over a field like this. Yani Q'nun dışına çıkmak istemiyorsanız elde edebileceğiniz en iyi form bu olur. Yani böyle bir şey olur. Tabii ki diagonal olabilir. Yani bu matris çarpanlarla vesaire. Genelde en iyi elde edeceğiniz şey olur. Bir tek bundan bahsedeceğim bir ara. Onun dışında kanonik formları bitirdik. Bu ama çok kullanılan bir şey değil. Çünkü yani bu matris her ne kadar basit gözükse de işlem yapmaya gelince çok da basit değil. O yüzden de hani bilmiyorum. Ben mesela hiç kullanmadım. 30 yıllık meslek hayatımda. Ama number teoride vesairede kullanılabilir. Hani eğer şey yapmak istemiyorsanız, field'ın içine çıkmak istemiyorsanız gerekir. Evet. Benim homepage'im.